Okay, welcome back. A quick logistic check-in on so both like group work and then also like project one. For project one, I had like a few dozen emails about like, hey, something happened, can't turn it in, this and that. Like there are no late penalties and there's no penalty for resubmission on any work. So if you make a mistake when uploading it, or a group member uploads only their own work and not your work, you can submit a new thing, like including everything, and there's no penalty for that. The other part to that is we're all working in groups and kind of learning to work with each other. So I'm gonna do a professional etiquette, it's a lecture, but sorry, just welcome to college, there's lectures. So especially when you're working in a group and you have deliverables, you have to include everybody in the group for communication. So emails or messages, include everybody. Because I had a few dozen emails that referenced a project in a group, but I have multiple classes and I wasn't even sure if it was part of this class or another class. That one's a separate issue about like writing clear emails, but include everybody in the group so everybody knows like, hey, for me, like Ryan couldn't do the assignment on Friday night. It doesn't matter why Ryan couldn't do it, but I couldn't. For me, why couldn't I do it Friday night? Friday night this whole weekend was kind of a mess with the big nor'easter. So like it's okay to just not do something as long as you have a plan to do it. So if you want to include me, great. If you're just trying to communicate with the group, include everybody in the group and say, hey, I can't get this done right now. I'll get you something by Monday. If you need help, then let us know like what kind of help you need. Like I need to talk to Professor Cooper about how to do it, or I'm going to read something about how to do this assignment. Like just give me 2 more days and I can get it to you. So those are the 2 main things of 1, include everybody in the communications. 2, clear action items. Like is this email saying that something needs to happen or that you just need time to get something done? Either way is okay, but do you just need a thumbs up or do you need actual like intervention? Again, a lecture, but professional. It's how the world works. Like when you get into professional work, is no one really needs to know like why things are late. It doesn't really affect them. What does affect them is like what help you need and when you can get it done, and that's all we need. And it's okay to have personal things where things get pushed off. That happens all the time. Have you ever seen a building get built on time and on budget? No. There's always something that comes up. Which one?
George Washington Bridge.
George Washington? I don't even believe it.
New York City. It was built below budget and below time because they were going to clad it with stone, but they didn't.
Oh, so they cut deliverables. They always cut something.
Yeah.
They either increase time or cut the deliverable. It's still a beautiful bridge. But that's okay. Anyway, that's the end of my professional etiquette lecture. Yeah?
What would you do in the scenario that somebody joins your group?
Yep.
Like your online group without like communicating with anyone right before it's due?
Yeah, that can happen, and we were just dealing with that issue in the last section. Someone was trying to join a group, but everyone had submitted something, so they couldn't actually get into any group. So the main thing that I would do, like if I was in a group and someone joins at the last second, is I would email or Teams message, whatever your preferred communication is, but get everyone involved and say, hey, welcome. Let's say I joined your group. Welcome, Ryan, to group 43. We all worked on these free body diagrams. Here's what we have so far. If you add yours, we can submit everything and be done with the project. That's how I would approach it. And I would still submit the work that I have and leave it up to them to kind of catch up to where the group expects them to be. That's how I would approach it. How does that sound for? And this is, again, I'll give the corporate pitch of, this is a real opportunity for growth on your part, like leadership growth, where you can take the initiative of like onboarding a new professional into your group. If you want the LinkedIn tagline of like what you did this semester that made you stand out from all the rest of the awesome UConn, because we do have really good students here. And things get pretty hectic throughout the school year. Cool. Other questions about either group work or specifically like project one? Like, did anyone else have issues or things come up? There's always weird edge cases. Or the entire thing is edge cases, right? Like there's always something. What I did not know was like if all the groups submit something, you just get excluded from all groups. Did you know this? So if you don't join a group, then you will get like kicked out of all groups. So it's like, join us. I guess you have to join us. Otherwise, we have to do some kind of logistical reassigning or rearranging. I'm not even sure. I'm not sure how to do it, but we can figure it out. But again, the main thing is communicating with everybody of like, if you're trying to join a group, but they already submitted something and you can't join it, include everybody in the group, include me, and say, hey, this is what I'm doing. Here's the work that I have so far. I want to be included in this group, and then it's a lot easier. Everyone's on the same page. We all know like, oh yeah, Ryan just dropped the ball this week and he's trying to join group number 22. 21. I like 3 and 7. 21. I'll join 21. Okay. Mid-level okay? No? Calm down, everybody. Not all at once. All right, let's do something fun then. Let's get into the next case problem where we can actually do some engineering. Wahoo! All right, let's zoom into our case to start. I don't love screenshots, but I took a screenshot because it's all hand notes anyway. But so this case we have actually, have you seen something like this before? Yeah? What is it? What is it? A jack? Scissor jack? Yeah, scissor jack. Nice. Yep. So some kind of scissor jack. Roughly, how does this thing work? Like, what's general sort of process?
Turn the screw.
Okay.
Faces the jack because it brings the two beams together.
Yeah, those two like big triangle lever arms, gets those closer together. Jack goes up. And why do you need a screw? What is the screw doing?
You get a mechanical advantage through it.
Okay. How does a screw give you mechanical advantage?
Well, there's a lot of the thread is like the helix shape is very long, so you
Yeah.
can find the distance actually gonna travel up.
Okay. Yeah. So long thread versus throw, like distance that we can send the thing. All right. So we kind of get it. I think we get it. Are there questions about how car jacks work? At least like initial, like how are we gonna use this? Any questions are okay. Like, why would you need a scissor jack? Why not use I don't know, something else? Different jack. A Joe, scissor Joe. Or Jill, scissor Jill. Something else. If there's more questions, we can go through those. All right, so our general kind of process is we are the engineers. We're trying to design this thing to lift a quarter of 1,300 kilogram. That sounds too big. I think I meant pound. 1,300 kilograms sounds like a lot. How big of a car is that? I guess it's only 2,600 pounds. That's not too big. That's fine. We're good. So a screw turns to bring the corners of these linkages closer, reduces the angles. Undefined. Oh, because it's LaTeX equations. That's annoying. I think. Yeah, why are they undefined? They are defined. What? All right, anyway. So the main goal is to determine the pitch of these threads and the length the lever arm needs to move. So like as we're actually like twisting this crank to move the thing, like how big of a crank do we need? So we're gonna split it into a few different steps. A kinematic description of motion, so like how the angles, the collar motion, and the lift height are all connected. A kinetic description that relates our screw, like how much load is in the screw, and the applied load from our car that's being supported. Then the third part is a kinetic connection between like our thread pitch. So we need some connection between how the number of threads per inch relates to mechanical advantage. And then the last part is a little bit of research. It could even be like experimental research of like pushing on a kitchen scale or on a bathroom scale. Like what is a normal load that you can sustain for so many thread, for so many like turns, something like that. So what forces can we apply? And then also like ergonomics. Like we can't make a crank that is as tall as a human, because then we're like comically sort of like turning this thing like this. So, and then if we make it really tiny, then we're gonna be dealing with like 1 million threads per inch for the same mechanical advantage. So something along those lines. All right, so I'm gonna zoom out some so we can see the whole picture. What is the difference between our kinematic descriptions and our kinetic descriptions? This was one of the first things we talked about, and it's a big part of dynamics, is like, can you separate those two concepts, the kinematic description and the kinetic description? Because they're connected, like F is still MA, but you need to be able to separate them and deal with one at a time and then connect them. So what's the difference here in this specific spot? Like what's the difference? You already know? Or thinking? You can think about it. Like
the kinematics are the acceleration, velocity, position. So it's
okay.
Position of the angle, position of the two sides of the jack close to each other, position of the top of the jack, and how it's accelerating and changing with whatever force, which is the kinetics, is the force we apply to the screw, and the force that's applied upward.
Okay, so do we need to know forces to know kinematics. That's one of our big questions. Like, is the only way to figure out acceleration with force. Like, can I describe, like in this case, if I know this collar is moving to the left at 5 millimeters per second, do I know how fast this is moving? Can I figure out how fast that's moving? That's the question. Or do I need to know how much force is applied? You can figure it out?
Yeah, if it's moving at 5 percent, just I think if you use trigonometry.
Some trig, okay, yep.
And also, the speed the top is rising is gonna change the further it goes in.
Oh, so there might be some like angle dependence depending on like if it's totally splayed out or all the way vertical. So there might be some dependence based on the shape of it, its current shape. That could be true. But but it sounds like those things we don't need the forces, right? Like we can, and this is the big part about kinematics. If you prescribe, if you're saying this thing is moving at this speed, it doesn't matter what forces are applied. You already said the thing's moving at a constant speed. So whether there's drag or friction or an ogre that's trying to grab it, like all that stuff adds up to zero because it's moving at a constant speed. So that's why it's important to be able to like split the two up and not start like, okay, here's my velocity, it's a function of force, position, theta, L, like split it up. So we're just gonna deal with geometry right now. What is the geometry of the motion? That's our first step. Sound good? And a lot of time, that's like 70% of the engineering dynamics anyway, is just how does this thing move, how do the parts interact? And then sometimes you send it off like, oh, it works, ship it. Don't even worry about the forces. Until you do, until it fails. So what do we think? How do we get started on what is the geometry of this motion? I know how fast this collar is moving. So what's going on with the rest of it? Take a second. You can either think or write things down, talk it over with somebody else, but what do you think you could get started with here? How do you connect all these moving parts?
Well, if you know, I know the thread pitch.
It's the CPI. So if you can figure out how far along the screw goes per second, you can figure out how many threads you travel per second, you can figure out how fast you're turning per second.
No.
Each thread is one rotation, each thread moves a certain distance.
So you know the rotation per second.
You can also relate how close they are together to two thetas.
Less than zero.
And then you can use theta to figure out the distance vertically from the bases.
My question is, you're in side class, and you know the pressure.
It's a manufacturing. There are 2 forms of manufacturing. What?
I wasn't being condescending, I was asking a different question. That's fine. Because that was me being like,
Okay, so can we think about equations? How do we relate? Let's start from there.
Is it accelerate?
How can we relate accelerate angular velocity to
Yeah.
thread pitch, I forget the equation for thread pitch, or how's it?
Yeah.
Yes, if you
The
can
pitch
definitely.
is normally
It's a
the
shame
shape
that.
that most times
That
the
T that
Fred's
solid
French or
just
Fred's
the distance that travel.
Most times Fred's per.
So threads count, for your threads count, would be count per unit length, we have, another thing
I mean, at
that's
least
count,
here,
which
the
is
same.
length
It
per
is
mile, and then we have another thing that is turns per time.
Just relating to W, I think V, we have in meters per second, right? So what, basically length per time. And we know that that's going to equal a certain amount of turns of the screw. So for each turn of the screw, we have a certain amount of angular velocity, which we can relate to rotation. So we can turn angular velocity into rotation per second. So we have rotations per second, which is velocity. And then thread pitch gives us meters per rotation.
Okay, so you're trying to relate.
So this is how we relate.
Okay.
Rotation per second times meters per rotation.
Yes.
So that's how we're going to relate thread pitch to the velocity. To the angular velocity.
Yes.
Meters per rotation
So
would
also
equal the,
V equals W times thread pitch.
and then meters per rotation, if you invert that to rotation per meter, you get the thread count.
Yeah.
Omega equals V times thread count to the negative.
Well, W is also, it depends on what unit it's going to.
We're gonna assume
We're
units.
gonna have to convert it into rotations per second.
Well,
Don't
yeah,
get to radians.
But, so that just be omega divided by,
These are
okay, so omega divided by 2
It all depends on what units we choose.
Well, yeah, but that's what we need to do.
That's why I thought of the fact that
Equals the velocity.
velocity at the top of the
Is it time? Times.
Yeah. Yeah, just kind of the sum.
Okay, so now we figured out that we work backwards to find the anchors, so figuring out how much we're trying to train.
Yeah.
Right, so it's 1 meter per second, and it's going to, let's say, 0.4 meters per second.
We don't even need point units, let's just.
I know, it's beta. That's one of those.
Okay.
So now let's figure out theta compared to the distance between them. So we have a certain distance between the two commas.
That's our velocity that changes.
Yeah. That's what you want to use.
3.5 pounds per meter.
And then you use the thread that's our speed that
We're screwing the screw.
how fast you turn.
How many rotations per second?
That's also
Whatever we're screwing it is. Like, yeah. Open that to the end, screw the screw long. Now imagine that. Screwing it.
That's what
So
we're
the
talking
rotations per second.
And then what we get.
Realistically, we want this to solve for B. Yeah. It's like in a way, like I was assuming, depending on the.
What did we have so far? So some initial thoughts. People were initially thinking about like what is the connection between thread, like threads per inch, let's say, and rotation rate, right? Like as you're twisting this thing, was that where some people were thinking? Yeah. So if we know how fast this thing is moving along the threads, then there's got to be a connection between how many rotations to get it to move that fast. Something like that. All right, that's a good thought.
We're not given a measurement between the two cups. Or like, I guess we have to assume.
So somehow, like, that velocity is proportional to omega. Like, say 1 rotation per second. That's usually like a normal human operating thing.
and then just multiply them.
Because I think.
What about connecting?
Regardless of the distance is 0 or 500, it will still go up the same amount. And it's a max height of 2L and a minimum of
How do I connect how high this thing is versus how fast this thing's moving?
I guess whatever this is, if we're measuring something, the joint is
Is there a connection, or can they move? Are those two separate questions? Like how fast does it
I mean,
move?
it's a relationship, but it's an order. It's a second order coordinate. It's a second order differential equation. that I don't want to make.
You think it's second order differential?
First order, sorry.
You think first order? Some kind of diffie Q?
Your meters per second changing numbers. So you're changing them.
Change length is related to this side is what we can measure.
Are there any?
And I'll try and
Did anyone look at this and see any like simplifying?
change in length here. We have a change in.
Like I know it's kind of already like engineering diagram, but
L cosine theta times this.
Yeah.
2L cosine
You can kind of break it into 4 different small triangles because they're all going to move at the same rate. You can just analyze like one triangle with one L.
okay. All right, so we could kind of split this up.
2L sine theta would be.
Were you thinking like these triangles?
You only need 2 is triangles.
Well, really, I'm thinking one.
Kind of as it's coming up, like 1, 2, 3, and 4,
Yeah.
something like that. How does that help for this one?
You can see how much the change in angle might affect like the change in height.
Yeah, so change in angle should have some connection to height. Is change in angle connected to that V? Like if I'm moving this thing to the left? It's got to have some connection, right? What we're doing right now, like we haven't kind of formally defined it yet, but we're dancing around this idea that this system is a 1 degree of freedom system. If you change one part of it, everything else has to change. So one way we could look at that is that theta is our 1 degree of freedom. Like if I know theta, I can calculate everything else. It might not be a quick thing, like maybe I have to plug it into a function, but everything depends on that one angle. Or we could say, whatever, the height also determines everything. So we could split it up.
First theta, and then we can use theta. That's what I meant. So
Um,
theta equals the inverse sine of our velocity over well, it not really the velocity, but the change in length, the side changes the so theta is the horizontal
this is
distance
triangle
traveled.
velocity. Which would just be the velocity times time. So the velocity at a certain.
So let's say I just take that right half and I redraw it. Are there constraints on these like moving parts? If I'm just considering them as like independent from, or not independent, but just like taking them as just drawing them, considering those triangles.
Like, they can, B can't be raised above 2L.
Okay, so there's two parts to that. One, you're setting like a limit to that, but a limit doesn't necessarily create a constraint. This is a weird pedantic thing, but that's why you're here in college, is like discuss weird pedantic things. So like one example might be if you throw something into a box, it can land anywhere inside the box, but it can't be outside of it. it still has 2 degrees of freedom because it can be literally anywhere in the box. There's an infinite number of positions that it can be, but it can only be inside this one like 10 centimeter by 10 centimeter square. So the constraint is that it has to land at the bottom of the box. So it's got to be height of 0 by time it's not moving anymore. So in this case, there is a limit, like it can't go, I mean, technically we could fold this thing over, but you were saying like you think it would buckle because now all the tension becomes compression and you'll probably buckle your support screw. So we do have a limit to that, like a limit on how far. What about constraints? Are there constraints on these bars? I like to label my hinges. Now it's O, A, and B. Do we know anything about O? Hinge joint. So it's gotta be fixed to the floor. What about A? Does A have any other?
A can only move in one degree. Yeah, can only move back and forth.
Only left, right,
Yeah.
And up, down.
and up, down?
A has the most freedom, B can only go up, down.
Well, it goes up, down, like related to the angle of out as well.
Okay. All right, think about it.
Along the arc.
How do we?
It's always a length away from bone.
So A has to travel like along this arc.
Yeah.
So A is always moving like along that arc, something like that. Okay. What do you think? What about B?
He's always moving in a straight.
Up and down?
E should be
B should be like just up and down. Because we don't really have that constraint in this case, but we have symmetry. Like,
Symmetry, so it cancels out.
yeah, so whenever we take away that thing,
No, I can't. Also the questions were asked.
kind of like this. So VB is now the motion of our support. VA is kind of like this person turning the screw to get the thing to lift up, get that jack in action. The jaction. So let's say we're moving 10 millimeters per second. If we're moving VA 10 millimeters per second, what is VB doing? How fast is this thing raising up?
Okay. Yeah. Is that an equal or it's two?
I just feel like we're skipping stuff. I feel like people want to figure out how the ink changes first.
You don't need how the equal changes.
Yeah. Okay.
Oh, no, you put, we technically do. This is a trigonometric problem where the relationship between VA and L is equal to the relationship change between VB and L.
L doesn't change.
Yeah, but that's the constant. That's exactly the point. So if you do sine, if you do the sine theta and cosine theta, each one in respect, I think it actually cancels out. I want to say. No, not quite. One is 90 minus theta times theta. Let's see. Moral aspect is going to be
So this is a great way to start.
cosine
Rather than trying to solve directly. Figure out
sine. And then with that makes is I multiply that sine. How does sine divide by cosine? So
Okay.
multiply by sine cosine.
Okay. Yeah.
VB tan is then because that's not like that.
And then the other side.
That's already not. You do need to.
Alright, so go ahead, remove this, the DXs.
So VAs are size over for
When the angle is 45 degrees, which makes sense.
Yeah. Yeah, and you're.
Because at 45 degrees, it goes in at the exact same rate.
You're gonna take derivative with
Just
respect to
change
time.
in distance between the 2 points.
And that'll give you a relation
But after that,
in straight on the last class.
So you're,
and then tan about 1 over tan
This should be
is
some,
right?
so if you're using like dx,
So,
then the other side. it should-
solving for VB is easy.
Yeah, no, yeah, well, that's great. Yeah, it's a nice, it's a great way to start, like, okay, I know how the like geometry lines up, because I can see these triangles. If I take the grid of that, now, I know
It's
how
just
changing
it's just a relationship between.
Yeah.
So you're just like, how does this side length change compared to that side? Here's this spring that you supposed to wasn't a spring.
Yeah, but that's like not. So actually, this
You know, I could have literally just done VA over VB equals tangent or whatever. I did it this way. I don't know why I did that. Because who needs to stay at home?
I have a light right
Yeah, I thought you're touching. There's an equal agreement.
What is going on behind that?
Yes. The only thing that's helpful.
Yeah.
It's
like into something.
The only thing that's helpful about memorizing it is that, like, I kind of understand how to use the equations more, but it's a lot of equations. So, and then a lot of like conceptual stuff too. So, camping not
We get out of here in 11 minutes, I think.
Yes, yeah, that's the atomic magic factor. Yeah.
I have.
Yes.
Thank you. I have no
Okay, so I saw something I found exciting, because I get excited about this stuff, but some of the starting points was kind of, rather than jumping straight into like, hey, I know this speed, let me calculate this other speed. It's like, all right, if I know how big this thing is, can I figure out how big something else is? Like, start with constraints on position, and if you know the constraint on position, you can figure out what the constraint on velocity is, if that makes sense. Like, if I know something always has to be 10 times t distance, I can take a derivative and figure out, like, oh, it's a constant speed, 10 times t. So let's start with that. How tall is this thing? How big is this? Yeah.
2L sine theta.
2L times sine theta? Is that right?
Yeah.
That's how tall it is? Where's your theta drawn? Is it the same theta?
Same as on the, like,
Same here?
yes, it would be.
Cosine?
Yeah.
Okay, that's all right. All right, cosine. How wide is this thing?
Unknown.
Unknown?
And impossible to calculate.
It's impossible, yeah.
With the given information.
Only God knows.
With the given information.
Vaya con Dios.
Well, it has to be greater than 0 and less than 2D.
Less than 2D?
Its maximum distance is.
Maximum's L, yeah. What's the minimum distance if it goes up to 90? 0, okay.
Well, technically.
Yeah,
So 0 to 90 would function as
0 to 90, yeah. A sine or cosine maybe. Arc sine, cosine. Yeah. Oh, that's a great question. How do we know that how do we even know that the height is 2L cosine theta? Where did that one come from?
Well, it's 2 bars tall.
Okay.
And then it is the y
We need-
component of that bar.
So, one of the first thoughts was like, hey, we can split it up into 2 triangles that are kind of sandwiched up against each other. So we've got triangle 1, which is, it's not L tall, but it's L times cosine tall. So that adjacent angle there. And we have 2 of them, so now we have 2L cosine theta. Thank you for asking, because I would imagine most people wouldn't jump straight to that conclusion. So thank you. L cosine theta, L cosine theta. So we have 2 of those, 2L cosine theta. So there's no way, we don't know how wide the triangle is? L sine theta? I like that. Yeah, it's still the same triangle, right? We're doing trig.
Yeah, 2L sine theta plus a constant.
You think it's 2L sine theta plus? Oh, you're saying like
Well, are we doing it two? It would be, we're doing one from.
Like this one?
Two separate things, closer. And it's also
Yeah.
the distance between the 2 points, like a constant like that we don't know.
Oh, I was just saying like in this little thing, like we kind of split it up into just these two triangles. We don't need like the two.
Well, that must be also good.
Then we can say L sine theta. But you're right, if we want to say like what is the total jack length, we would have two L's on either side plus whatever mounting distance we had. All right. So this is something that maybe you haven't seen before and maybe haven't had to deal with it before, because like this is the first time that you're dealing with like moving systems, like dynamic systems like this. If I know constraints on position, I know the constraints on motion. And I'll say that again. If I know constraints on position, I know the constraints on velocity, because velocity is the change in position.
Because our position, where it's going to be, we call the position, or you call the x.
Yeah.
Equals length times sine theta. If you just apply that length, we get that.
So, like, what is our position of RA and RB? Where are these things? I guess we could give it a reference frame, right? /O. What are they? What is RA? So I like to label my hinges because I just like to give them names. I'm not very creative, so I didn't name them like Ernest and Hemingway. I don't know. But I just said, here's O, there's A, and there's B. It's like, just so whenever I'm on the top hinge, you know, the bottom hinge.
We're saying distance from A to the origin, from B to the origin.
Yeah. Yeah, what are those?
A to O is always L, and then B to O is always the height.
Always H?
Yeah, RB is equal to H, and then RA is equal to L.
A dash.
Like this? So they're vectors, right? Position should be a vector. So we know magnitude.
Oh,
Magnitude is definitely L, and it's definitely H. What direction are these?
H is always going to be, we have to find a coordinate system that's straight directly away, so.
it would be HJ hat.
Yep, we could say like HJ hat, like this, right? So I can say like my origin is O. There's an I, there's an X coordinate, there's a Y coordinate. So B I know is always just H right above it. And H is 2L cosine theta. And again, we kind of circled around this idea, but we settled on these equations of if I know theta, I know everything about this system. I know how wide it is, I know how tall it is. So it's a 1 degree of freedom car jack kind of system. Cool. What about direction of A? Where is A? How do I know?
Given it polar, it's always radial.
Yeah. Oh, yeah, we could just say it's L E R, like that, in polar coordinates. That would be fine. We could say that. I'm down with that. But then we have to define velocity in terms of polar coordinates. Do we want to do that too? It's not bad. No, it's fine. I like polar coordinates. All right. ER is, there's always the same, oh, we have 1 minute, sorry, and you have an exam, at least some people do. We have 1 minute left. This was, believe it or not, this is like the hardest part, is trying to get to what are the constraints on this system. So once we're here, there's math to get to the next steps, but this is the biggest part of the kinematic analysis. It's like, how do I describe constraints on position and then start working towards everything else? So nice work. This was great, very good start. Then we'll pick up on Friday. Thanks a lot. Good luck on the exam.